Okay, we're going to get started on acids and bases, so this should be fun. Um, we're kind of building up to what I think is probably the hardest unit of the year. Just definitely the most new stuff and just very complicated type problems. This is not it, though. This is just kind of a lead up to that particular chapter. So we need to make sure that we understand everything about acids and bases before we go on to the next thing, or the next thing is going to be very confusing. So we're just building a foundation here. This shouldn't be that difficult, especially this particular set of notes. There's going to be a lot of review in here. Okay, so we'll go through this pretty quickly, just to touch on some of the things that you need to know about acids and bases. So first of all, properties of an acid. You may or may not know some of this stuff. Acids tend to have sour taste. So you think about some of the common acids that we eat, vinegar or citric acid that's in fruits, that sort of thing. That's kind of what gives it that sour taste, is the acid itself. They can cause certain dyes, which are called indicators, to change color, which we've already done a lab this year where we used an indicator called phenolphthalein that changed clear in the presence of an acid, changed pink in the presence of a base. They will react with metals to form hydrogen gas. Okay, anything above hydrogen on the activity series. I'm going to show you some examples in your AP questions this time around of ways that they like to ask this question on the equation writing section. Okay, so you need to know this concept. And they will conduct electricity in aqueous solutions to some extent. At least it depends on how well it conducts, depends on whether it's a strong acid or a weak acid, which we'll get to later. Okay, but they are electrolytes. That means they do dissociate into ions in solution, and so they're going to conduct electricity. This is the activity series, okay, which you do not need for the AP exam, because if they give you a reaction on the AP exam where a metal's reacting with, hydrochloric acid or another acid, they're going to give you a metal that can replace the hydrogen. Okay, so a common one is zinc is placed in hydrochloric acid, and so zinc, notice, is way above hydrogen on the activity series, so it can replace hydrogen and form hydrogen gas and zinc chloride. Okay, so those are the kinds of things that you might see on the AP exam. We'll talk more about that later. Bases. You probably have less experience with tasting a base. They do taste bitter. Most bases are going to be, more like household cleaning products or that sort of thing. A base that you may have tasted is baking soda. Baking soda, some people brush their teeth with it because it's very gritty and it's supposed to help clean the teeth well. So, if you've ever brushed your teeth with baking soda, you know that it doesn't taste very good on its own. They have a slippery feel. So kind of like a soapy, when they're wet especially, they'll have like a soapy feel to them. Again, they cause indicators to change color, like the phenolphthalein. And they will also conduct electricity in an aqueous solution. And again, the extent to which they conduct depends on whether they're strong or weak bases. Okay. Just a couple definitions of acids and bases. We've already talked about one called Lewis acids and bases, and I'm not going to touch on that a whole lot here. We will review over that on the AP questions this time around, just to make sure you remember that definition. But Arrhenius was the first one who really came up with a definition for acids and bases that was used in a widespread way. And Arrhenius basically said that anything that increases the H plus ion concentration when dissolved in water is an Arrhenius acid. So an example of that is hydrochloric acid, again, because you put HCl into water, and as soon as you do, it splits apart into H plus and Cl minus. And as we're going to see on the next video, that's a little bit of a simplistic explanation, and I think we've already talked about this, how it's really probably more that this H goes and joins onto an H2O that's already in existence and makes H3O plus, and that's a more accurate depiction of what's really probably happening there. But the idea is it's going to increase the H plus ion concentration or the H3O plus ion concentration when you put it in water. Okay, and then an Arrhenius base is something that increases the OH minus concentration when you put it in water. So an example of that is NaOH. So you've got sodium hydroxide, and that splits apart into Na plus and OH minus. Okay, and so that's your Arrhenius acid, Arrhenius base definition, and that works for most of the things that we're going to talk about in this class. Or I guess I should say it works for a lot of the things, but not everything. Okay, it's not really a wide enough definition to define all acids and bases, because if we're thinking of acids and bases, acids as things that lower pH and bases as things that raise pH, then that doesn't completely tell the whole story necessarily. The problem with the Arrhenius definition, it limits the definition of an acid and base to something that's in a solution, which again, most of the time in this class, that's what we're going to be talking about. Okay, but when you breathe in hydrochloric acid gas, HCl gas, that does not increase the H plus ion concentration in a solution, but it's still going to burn your nose. Okay, it still acts like an acid. So in the same way, sodium hydroxide is little solid pellets. You touch that as a solid and it's going to burn through your skin. It's going to act like a base even though it's not increasing the OH minus concentration of a solution. Okay, so we need a more general definition here. The Bronsted-Lowry definition, just a few things here with the Bronsted-Lowry definition. And again, this is not the most broad definition either. Okay, the Lewis acid-base definition is really the most broad, and we've already learned that one. And again, we'll talk about that more in class. But the H plus ion in water, when we put an acid into water, the H plus is going to separate from the anion in the acid. Okay, and that could be any number of things. It could be HCl, could be HF, hydrofluoric acid. It could be acetic acid, C2H3O2. Okay, whatever it is, you've got the anions here. Okay, and then you've got the hydrogen. And so when you put these into water, the H plus is going to dissociate or separate from the anion. Okay, H plus is just a proton. All right, there are no electrons. Because if you think about hydrogen has one proton and one electron. So to become an H plus, it needs to give up its only electron. So then it's essentially just a proton. Okay. But what typically happens there, as soon as that dissociates, like I said before, is this H comes and attaches itself to an existing H2O molecule in the solution, and what ends up happening there is it makes hydronium, H3O plus. Okay. So that hydronium forms when H plus from an acid joins with a water molecule. So what can happen here, when you have this H3O plus, it can sort of exist by itself, or it can become surrounded by water molecules, because now this thing has a charge, right? And remember, water likes to surround ions, okay? And so when that happens, it can make these large clusters, and H5O2 plus and H9O4 plus. I'm not sure that I like those designations that much, because it sort of seems to imply that this is a 5 hydrogens and 2 oxygens all chemically combined. What it really is, it's an H3O plus with H2O molecules surrounding it, and there's hydrogen bonds there. Okay, so H5O2 plus, again, it's really, this is the H3O plus part, and then this is an H2O molecule that is attracted to it. This oxygen, which has a partial negative charge, is attracted to the partial positive on one of the hydrogens here. Okay, and then the same thing with H9O4 plus. Again, these are hydrogen bonds here, not actual chemical bonds. So I'm not sure that I like calling it H9O4 plus, but there you go. Okay, so the Bronsted-Lowry definition then is going to be a proton donor versus a proton acceptor. So a proton donor it's an acid. Okay, that means that it's giving an H plus to another substance. It's donating a proton. Okay, and that's a little bit broader definition that works outside of the confines of just a solution. Okay, and so that's, you know, that's a good definition. And this will work for pretty much everything we do. The only thing that it really doesn't work for in this class is the coordination compounds, the complex ions, where a transition metal actually just accepts a lone pair of electrons from something else, and there's really no hydrogen involved whatsoever, but we still define those as acids and bases. That's where this definition does not work, okay? And so, again, we already talked about Lewis acids and bases, and the reason we talked about it is because we already talked about coordination compounds. So, that aside, the Bronsted-Lowry definition of acids and bases will work for pretty much anything else that we're going to talk about in this class, okay? So, a proton donor, that means that it's giving away an H plus to something else, okay? If it does that, it's an acid. If it accepts a proton, an H plus, from something else, then it is a Bronsted-Lowry base. It's a proton acceptor, okay? Bronsted-Lowry acids and bases always come in pairs, okay? The H plus doesn't just leave something, it goes somewhere. All right, so you can't just have, it's kind of like an electron, right? Like we learned this with ionic compounds. An electron doesn't just leave a cation for no reason. The reason that it's leaving a cation is so that it can go to an anion. Okay, so that's the way that that works. These pairs, well, we'll get to that in a second. We'll talk about conjugate acid-base pairs. Okay, but here's a couple examples. All right. First example here, you've got HCl plus H2O. Okay, so when you have HCl and H2O, this is a little bit weird here, and we're going to talk about this more on the next video as well. But this is the acid. That's fairly obvious because we've got a hydrogen in front here. Now, we do have a hydrogen in front of the H2O also, which kind of makes it look like maybe H2O could be an acid or a base, depending on the situation, and that is actually correct. But for now, it's actually going to act like our base, because this hydrogen is going to go onto this water. It's going to form H3O plus, and we'll have Cl minus, okay? Now, notice, this is the acid because it is the proton donor. It's giving away the hydrogen, okay? H2O in this particular case is the base because it is the proton acceptor. Alright, it's the one that's accepting the hydrogen. Alright, and then another example here, HCl. Again, obviously this is going to be the acid because hydrochloric acid is an acid. But what's going to happen here is this hydrogen is going to donate its proton to NH3, okay, which turns out to be a fairly common base. Ammonia is a base. And so, now again, notice, these are not taking place in solution. So these technically would not be Arrhenius acids or bases because, you know, this is not increasing the H plus ion concentration in a solution, but it is donating a proton to something else, okay? And so what we'd end up with here is Cl minus plus NH4 plus, okay? And so that's the idea. The second reaction here, it's what causes the film on glassware in a chemistry lab. It contains strong acids. So what you end up with is basically this NH4 plus and the Cl minus. They actually, if we're doing this outside of a solution, they actually will combine and they will form NH4Cl solid, okay? And ammonium chloride, that's, you probably have never seen this, but if I leave the 12 molar hydrochloric acid, you know, a beaker of that sitting out for too long, then it's actually going to react with some of the ammonia in the air, and this will actually make this ammonium chloride on the outside. And it looks like a film on the outside of the beaker, and you're afraid to touch it because you don't know if it's going to burn you or not. Okay, so just again, another little example here talking about Arrhenius versus Bronsted-Lowry, okay? So NH3 in this particular case, in an aqueous solution, when you add that to H2O, I forgot the subscript and superscript here. This is NH4 plus and OH minus. Okay. Now notice what the NH3 did. It actually took a hydrogen from the water. Okay. So it's an Arrhenius base because notice what it does do. The net result here is that we end up with more OH minus in the solution. So because it increases the OH minus concentration. Okay. So it technically is an Arrhenius base. The Arrhenius definition does work in this particular situation for the base. Okay. NH3 is a Bronsted-Lowry base because, and again, the definition there, what makes a Bronsted-Lowry base a base is that it is a H plus or a proton acceptor. Okay. And so, because it accepts the hydrogen, or the proton, from the water, that makes the NH3 the Bronsted-Lowry base. Now, H2O is not an Arrhenius acid, because an Arrhenius acid increases the H plus concentration in the solution. There is no H plus in this solution on the second side here. You can see that. So, the Arrhenius definition does not work here, okay? But H2O is actually acting as a Bronsted-Lowry acid because it is an H plus, I guess I should put it in, H plus, or a proton donor in this case. It's giving away the proton. Okay, so you can kind of see the difference between those definitions with this example. All right. If a substance can act as an acid in one reaction as a base in another, it's called amphoteric. I thought we weren't going to get to this till the next set of notes, but here it is. Water is an example. Okay, we've seen two examples here. One right here at the top, HCl plus H2O, where water is acting like a base. Okay, and then we also saw an example here where water is acting like an acid. So water is amphoteric. It can act as an acid or a base. Okay, it acts as a base when it's combined with something more acidic, and acts as an acid when combined with something more basic. If an acid and a base differ only by the presence or an absence of a proton, they're called conjugate acid-base pairs. Okay, the definition of this isn't going to make a ton of sense. I'm going to show you some examples, and then I think it will. Most acid-base reactions are at equilibrium, so probably in every reaction you're going to have two things that are acting as acids and two things that are acting as bases in each of these solutions, depending on which direction they're going. Okay, so here's an example. So let's figure out what's going on here. Okay, so we can think about this reaction in two directions. First, in the forward direction. Okay, in the forward direction, what's happening here is this hydrogen on the HNO2 is being donated to the H2O. Okay, so in that case, this is the acid. The water is the base. Okay, the acid is donating the proton, the base is accepting it, or that the water is accepting it. We can also think about this in the opposite direction, okay, because this reaction is in equilibrium, so we can think about the reverse reaction that's happening here. And in reverse, to reform the reactants, this hydrogen is now going back to the NO2 minus. So in this particular case, this is going to be the conjugate acid. Okay, because it is acting as the acid on this side to reform the reactants. Okay, and so this one's going to be the conjugate base. So the way we usually pair these things up, we say, okay, here's an acid and its conjugate base, right? These two things are related because you've got HNO2 forming NO2 minus, and then NO2 minus going back to HNO2, okay? And then this is the base and its conjugate acid, okay? And those two things are related to one another. So hopefully that makes sense, but that's kind of the idea. We can set these things up in pairs and say they're kind of going back and forth. So the water is accepting a hydrogen, and then it's redonating a hydrogen, so it's kind of acting as the base and the acid at the same time. Okay? Conjugate base of each of the following acids. All right, so HClO4 is an acid, so its conjugate base would be just ClO4 minus, okay? That's because at that point it is given away a hydrogen, okay? And then it could re-accept a hydrogen for something else later, okay? H2S, its conjugate base would be HS minus, okay? It could maybe be S2 minus if it gave away both its hydrogens, but more likely it's going to just give away one hydrogen and be HS minus, okay? Again, I forgot to superscript everything here, but pH4 plus, its conjugate base would just be pH3, okay, with no charge, because we get rid of one hydrogen. Now we have, you know, one less positive charge there, so it's just pH3. And then HCO3, that's wrong. HCO3 should have a minus charge, so the conjugate base there would be CO3 2 minus, okay? Alright, so those are the conjugate bases, and then the next one asks what are the conjugate acids of each of the following, okay? So if we've got Cn minus, then that's a base. It's going to accept a hydrogen, and then it's going to be HCN, okay? And then HCN is the conjugate acid that can turn around and reform the conjugate base by giving away that hydrogen again. The conjugate acid of SO4 2 minus, again, most likely it's going to be HSO4 minus. You could say H2SO4, but it's more likely that it's just going to gain one hydrogen from something rather than two. The conjugate acid of H2O, we've already talked about this one, would be H3O plus, and the conjugate acid of HCO3 minus would be H2CO3. Okay. Now notice something about HCO3 minus. That's what we call amphoteric, because up here it acted as a base, sorry, as an acid. Did I go the wrong way with that before? Conjugate? No, I'm sorry. Okay, so it's acting like an acid here. Okay, by giving away its hydrogen and forming CO3 2 minus. Down here, it's acting like a base and accepting a hydrogen from something and forming H2CO3. Okay, so that's also amphoteric, like water is. Okay, more sample problems here. The hydrogen sulfide ion is amphoteric. We want to write an equation for the reaction of HSO3 minus with water, in which the ion acts as an acid. And then we want to identify the conjugate acid-base pairs. Okay, so we've got HSO3 minus plus water. And because we're talking about conjugate acid-base pairs, this is going to be an equilibrium reaction. And that's the main reason we talked about equilibrium last chapter before we started acids and bases, is because most acids and bases happen in an equilibrium with one another. So we want to think about where the HSO3 minus is acting like an acid. Okay, so if it's acting like an acid, that means it's giving away a proton. It's donating a proton. Okay, so it's donating a proton to the water here, so we're going to end up with SO3 2 minus on this side plus hydronium, H3O plus. Okay, and then I didn't leave myself a lot of room down here, but this is our acid here. This is our base. This is going to be our conjugate base. Okay, and this is going to be our conjugate acid. So then if we're going to pair these up, the acid and its conjugate base, that's the pair right there, okay? And then H2O, the base, and its conjugate acid, H3O plus, okay? So that's how those pair up. Alright, I'm going to have to erase this so that I can read the next one here. And then we're going to do the same thing again here, except we're going to think about, okay, what if the HSO3 minus reacts with water and acts as a base instead? Okay, because what we have here, this doesn't usually happen, but if you have two amphoteric things, then both of them can go either way as far as acting like an acid or base. And so this one particular situation, we can have it happening, you know, We can think of it happening either way. So the other thing that could happen here is that this HSO3 minus acts as a base and takes an H from the water, forms H2SO3 plus OH minus. Okay? So again here, now this is the base. The water is acting like the acid because it's donating the proton. This over here, if we think about the reaction going from right to left in the reverse direction, then this is now, oops, this is now the conjugate acid, and OH minus is the conjugate base. Okay, so you get your base and your conjugate acid, there's a pair, and then your acid and its conjugate base, and that's a pair. Alright, so that's how you pair those things up. When lithium oxide is dissolved in water, the solution turns basic from the reaction of the oxide ion with the water. Write the reaction that occurs and identify the conjugate acid-base pairs. Okay, so lithium oxide, this might be the kind of question that you get asked on AP exam on the equation writing section. Lithium oxide is Li2O, okay? As soon as we put this in water, it dissolves. Okay, now we should have known that because lithium is an alkali metal, so it's going to dissolve in water. When that dissolves, it's going to dissociate, split apart into Li plus, and O2 minus, okay? Now the lithium in the water doesn't really do anything, but the O2 minus in water actually does. And we're going to learn more about this towards the end of this chapter, okay? But O2 minus here, it's saying that it reacts with water, okay? And we want to talk about the reaction that occurs here. This is going to be probably less of an equilibrium, but it will be an equilibrium. So you've got this O2 minus, fairly unstable because it's got a 2 minus charge, right? So what can happen here is the water can donate a proton to the O2 minus, okay, which honestly it's not so much the water donates a proton to the O2 minus as the O2 minus is so unstable it starts taking hydrogens wherever it can find them. So what you end up with here is actually OH minus plus OH minus. Okay, so a fairly strongly basic solution when you put lithium oxide into water. Because it makes a bunch of OH minus. Now, this is weird, okay, but on this side, it's fairly easy to see. Okay, oxygen is the base here because it's taking a hydrogen from the water, and that makes water the acid. Okay, but then over here, we've got two of the same things, and in order for this reaction to go back in the reverse direction, one of these has to be the conjugate acid, and one has to be the conjugate base. Okay, so it doesn't really matter which one of these you attach to which, because I don't know which is which here. But in order for this to go back in the reverse direction and reform the O2 minus and the H2O, one of these OH minuses has to actually give a hydrogen back to the other one. And that just doesn't happen that often, okay? So, I'm writing this as an equilibrium. Most of the time, I mean, this equilibrium is going to be very, very much shifted this direction towards the products. It's not going to go back towards the reactants very much, okay? All right, relative strengths of acids and bases. So the stronger an acid, the weaker its conjugate base. The weaker an acid, the stronger its conjugate base. I'm not going to spend a lot of time on this right now because we are going to talk a lot more about weak acids and weak bases. 3 categories of acid-base strength: strong, weak, and negligible. Really, these are the 2 that we care about, okay? So there are certain things that, they have hydrogen in them, but they really don't give away those hydrogens. They're maybe attached in such a way that it's not favorable for them for the hydrogens to leave, okay? So there are certain things that have hydrogen in them but don't really act like acids or bases. The strong and weak, those are the 2 that we really care about. We've talked about these before. Strong acids are strong electrolytes. They completely dissociate in water, okay? their conjugate bases tend not to reaccept protons. So strong acid-base reactions we typically don't write as equilibrium because they usually don't go back the other direction. Weak acids and bases only partly transfer, and what that means is, only some of those molecules will actually transfer their protons to the water. So they partly dissociate, some do, some don't, and then their conjugate bases will sometimes go back in the reverse direction. So these will usually write a forward arrow for, these will write an equilibrium for, okay? And again, we will get into that more later. We can determine the side of the reaction the equilibrium favors, okay? In every acid-base reaction, the position of the equilibrium favors the transfer of protons to the stronger base, okay? So, and again, we're going to talk more about this stuff. So let me give you a couple examples here, and then, is this it? Okay, we're almost there. I just need to hurry up. So we've got HCl plus H2O, and that's going to yield H3O plus and Cl minus, okay? So what it's saying here, okay, the position of the equilibrium is going to favor the transfer of protons to the stronger base, okay? So in this particular example here, HCl is going to give away its proton to the H2O to form H3O plus and Cl minus, okay? The position of the equilibrium, it's going to favor making the stronger base, is what this is essentially saying, okay? So what that means is, if you look at the two bases in this thing, this is an acid, HCl is an acid, H2O is a base. This is the conjugate acid here for water, and Cl is the conjugate base, okay? So we've got two bases here. We've got H2O and we've got Cl minus, okay? Now, you may not be able to tell just by looking at that, but you also probably can. Cl minus, that has a negative charge, okay? That's a little bit unstable, and for that to accept a proton is a fairly likely thing, okay? So that Cl minus is actually a stronger base in this particular case than the water, okay? And so the equilibrium is going to favor the formation of, see, this is a bad example. I don't know why I put this example on here. Because the HCl completely dissociates, it's not going to come back together. Just 1 second, I'm going to look this up to make sure I'm telling you the right thing here. Okay, sorry about that. Let me back up here for a second and just say I was making a bad assumption here, which is that Cl minus, because of its negative charge, is going to be a stronger base. But that's actually not the case. What I wasn't thinking about was the relative electronegativities of the oxygen versus the chlorine. And so actually H2O is a stronger base in this particular case than the Cl minus is, okay? Because oxygen is a little bit smaller. Oxygen is basically the second most electronegative thing on the periodic table next to fluorine. So its ability to attract hydrogens to itself is much greater than the chlorine. So that's kind of the reason why the H2O is actually a stronger base than the Cl minus, okay? And because of that, that does mean that this is going to tend to happen more often than this, okay? You can probably think about this in the opposite direction as well, in terms of the relative strength of acids, which might be easier to think about. We know hydrochloric acid is a strong acid. Because it's a strong acid, it's going to completely dissociate. It's not going to want to go back the other direction. That kind of makes more sense in my mind. But if you want to think about the which one's a stronger base than another, you need to remember the concept of electronegativity. Okay, and so that's going to kind of help guide you on whether something is going to be able to, pull a proton towards itself or not. So let's look at the second example here. I think this is maybe a little bit easier to see. This HC2H3O2, again, the acid here is the acetic acid, and that makes the water the base again. Okay. This is the conjugate acid, and the conjugate base. Okay. And so if you take a look at those, and you want to know which direction the equilibrium actually favors in this particular case, in this case, the C2H3O2 minus is a stronger base than the water. Okay. And again, there's actually a chart in the book that helps you with the relative strengths of acids and bases. So that could help you. I'm not sure that I like this particular way of thinking about it, because it sort of does involve a little bit of memorization, because sometimes it's just hard to look at these things and know which one's going to be a stronger base than another. So they won't typically ask you this question on the AP exam, but it's just kind of worth mentioning that the direction of the equilibrium is influenced by this. Okay, so because in this case the C2H3O2 minus is a stronger base than the water, then the equilibrium is going to predominantly lie in this direction. I don't know why I made a curved line there. Okay. But there are going to be more reactants in this equilibrium than there are products. Okay, because this C2H3O2 minus tends to accept a hydrogen from the H3O plus more often than the water tends to accept a hydrogen from the acetic acid. Okay. And so what you're going to end up with there is a fairly small equilibrium constant, a fairly small K, because there's going to be more reactants than there are of the products. Okay. Predict the products of the following acid-base reactions, and also predict whether the equilibrium lies to the left or the right. So we've got one here, HCO3 minus plus F plus, or F minus. So what's probably going to happen here, the F doesn't really have any protons to donate, so going by the Bronsted-Lowry definition, the hydrogen is probably going to go to the F here. Okay, so then we're going to end up with HF plus CO3 2 minus. Okay, and again, if you're using that chart in the book, then you can kind of see this. It's on page 618. Let me get this chart a little bit closer to myself so I can actually see it here. So we're looking at the relative strength of the bases, okay? And the bases in this situation, the F minus is a base because it's accepting a hydrogen from the HCO3 minus. The other base here is the CO3 2 minus, okay? So you can look at F minus versus CO3 2 minus, and the stronger of those two is the CO3 2 minus, all right? So this equilibrium is going to lie to the left. Okay, there's going to be more of the products than there are, or sorry, more of the reactants than there are of the products. Okay, because this is going to have more of a tendency to happen because the CO3 2 minus is a stronger base. The next one here, the O2 minus and the H2O, is going to make OH minus and OH minus. We already talked about that one. The bases here are, no, sorry, the bases here, because the hydrogen is going to the oxygen, so this is one of our bases, the O2 minus, and then one of the OH minuses over here is also a base. So then you can compare those on the list. O2 minus is a pretty strong base. It's just barely stronger than OH minus on this chart on page 618. So what that means is, because the O2 minus is the stronger of the two bases, that it's going to tend to accept a hydrogen from the H2O, and this side is going to kind of predominate. So we're going to have more of the product. Okay, and then the last thing here, well, HS minus is kind of amphoteric. It could go either way, but the acetic acid, that's an acid, so this is going to tend to give away its proton, which means that the HS minus in this case will probably be a proton acceptor. So that's going to end up being H2S plus C2H3O2 minus. Okay, so then the bases in this situation are the HS minus, because that's the proton acceptor, and then on this side, C2H3O2 minus is the other base. So you're comparing those to one another. And it looks like in this case the HS minus is a stronger base. So since it's a stronger base, it's going to tend to accept a hydrogen from the acetic acid more often than the C2H3O2 is going to accept a hydrogen from the H2S, which means the equilibrium is again going to lie in this direction towards the products. Okay? Alright, hopefully that makes sense. Sorry about that confusion. I forgot that chart was in the book, so I was trying to figure out just on my own the strength of those acids and bases. You don't need to know that. You can use the chart for any example problems we do in class, and I'm not going to ask you that kind of question on the AP exam. If I ask you a question, on the test, if they ask you a question on the AP exam or I ask you a question on the test about that, we will give you the K, and then you'll be able to tell me which direction the equilibrium lies. Okay? Alright, so that's that. Sorry that one was longer than I intended it to be. There's just a lot to talk about with the intro to acids and bases here. But we'll see you in class.